Hello! Welcome back. After following this video, you'll be able to move your triangle around in 3D space, as well as being able to move around a camera. Depending on how you set up your values, you should see results similar to what I have shown on the screen right now. 3D transformations require complex 3D math, which we don't have to write any of it. We will be using GEML, and GEML has all the math that we require, implemented plus more. When transforming an object around in 3D space, we need a way to represent its transformation. We need a position, a rotation, and a scale to represent its transformation. So let's go ahead and create a class called Transform. This class will have 3 private variables. The first one being a vector3f, and we'll call it position. The second one will be a Quaternion f, and we'll call this rotation. And the last one will be another vector3f called scale. The vectors give us 3 float values that represent x, y, and z. Then we have the Quaternion. A quaternion is an extension to complex numbers. In computer graphics, we use these to represent rotation. There is another way to represent rotation using Euler's angles, which is rotation represented by pitch, yaw, and roll. However, this route is susceptible to gimbal locking, which means we lose 1 degree of freedom for rotation. Now, lock is definitely a misnomer, and it can always gain that freedom back, but we have to find another order of rotation to compensate the gimbal lock. That's just too much work. Simply put, quaternions work in a way that avoids gimbal lock due to its complex nature. Since it's implemented, we'll have no problem using them. So let's go ahead and create the constructor of our transform class. And we'll go ahead and set position to a new vector3f, rotation to a new Quaternion f, and scale to a new vector3f, and we'll pass in 1 for the scalar. The way we have initialized this, it's basically set in the transform to the center of the world with no rotation and default scaling, which is 1. If this was set to 0, then nothing would be shown. So let's go ahead and create some getters and setters. And we are almost good. We need to create a function that retrieves the transformation. You might be thinking, why? We have the getters for these. Can't we just call it a day? My answer to that is no. I call it transformation. Okay, terrible jokes aside. We need a way to combine all of these values into 1. This way, we can combine multiple transformations. This function will return a matrix 4f, and it will be called GetTransformation. A matrix 4f is a 4x4 array of values, whose multiplication process really gives it its value. It's also order dependent as well, so keep that in mind. I like to think of one matrix as its own world, and we can transform the worlds to our heart's desire. So let's go ahead and create our so-called world, and I'll just call it return value. Goes new matrix 4f. So the first thing we want to do for this world is we want to translate it. So let's go ahead and use return value and call translate. Then we can just pass in position. Then we can call rotate and pass in our rotation. Then we can call the scale and pass in scale. And then we return it. These functions simply multiply matrices internally, so we don't have to make new matrices and multiply them together ourselves. Doing multiplication out of this order will yield some pretty weird results. I recommend you giving this a try so you can see what happens. This is pretty much it for the transform class. We can go ahead and create the camera class. Anything involving 3D graphics has a camera. This camera has its own transformation and has another special item that gives it that 3D view, a projection. The camera will have 3 private variables, a vector 3f for position, a Quaternion f for rotation, and a matrix 4f for projection. Let's go ahead and create our constructor and initialize the variables. After initializing these variables, we now have a 2D camera that is literally positioned in the center of the world with no rotation. When initializing the matrix like this, it's giving it what's called an identity matrix, and it basically looks like this. All ones diagonal. This is basically the 1 value of a matrix. And if we just kept our projection looking like this, then we'll have exactly what we have now. So let's go ahead and change that. The first thing I'm going to do is generate some getters and setters. We'll generate getters and setters for position and rotation, and we'll only have a get projection instead of a set, since we'll have 2 different functions for that one. So now we got our getters and setters, almost all the setters. We need to initialize the projections. I'll start off with the orthographic one. I'll call it set orthographic, if I can spell. And we need to pass in 4 floats for arguments. We'll want a left, a right value, a top value, and a bottom value. And essentially, the left value is how many units from the center of the projection to the left side of the screen. And it works the same with right, top, and bottom. To set the orthographic, all we got to do is use projection to call ortho. I actually like calling set ortho 2D. And that's pretty much it. Set orthographic creates a nice 2D plane, so you can basically create a 2D game. But since we're going with 3D graphics, an orthographic projection is useful for GUI elements. GUI elements. So let's go ahead and create that second setter. And I'll call this one perspective. And this one is going to give us that 3D look that we're going for. The first value we're going to need is a float FOV. If you are unfamiliar with this value, it's field of vision, and it's basically the angle. It's basically the viewing angle. You can only see things within this cone that you're projecting out. The next one is going to be a float, and it's going to be called aspect ratio. Aspect ratio is going to either be the window or the image that you're rendering to. This way it keeps the projection looking normal and not odd. The aspect ratio is basically width divided by height. The next value is going to be z near, and the last value is going to be z far. And these are basically how close and how far the camera can see. Z near you would think you would put at 0. Oh, we'll just put it right next. We'll just put it at 0. We want to see it as near to the camera as possible. But you're not going to be able to do that, and Java's going to throw some exception, a division by 0 exception, I believe. And that's because there's division going on with it. And you can't divide by 0. It's impossible. So we need to set that to a value that's very close to 0. But we'll do that when we get there. So we can use projection, set perspective. We'll pass in FOV, aspect ratio, Z near, and Z far. And that's it for the projection, and that's almost it for the camera. Now, the camera needs its own GetTransformation. So we'll have another get matrix for F, GetTransformation. This time, though, we're going to be doing our transformations a little differently, because we are not transforming the camera. Instead, we are transforming the world. So the camera is essentially going to stay at the origin. It's going to have no rotation. And instead, we're going to transform the world. So how do we do this? Instead, rotate the world. We're going to rotate by the rotations dot conjugate. And make sure you pass in a new quaternion as well, otherwise it's going to affect our current rotation. We don't want that. Then we're going to translate by position multiply by -1 into a new vector 3f. Because we need to translate the world to the camera, if we translate this camera forward, the world is going to be translating itself backwards. If you were to rotate the camera, let's say 45 degrees to the right, well then the world is going to rotate the opposite direction. So let's go ahead and return the return value. And we are done with the transform class and the camera class. Up next is to mess around with our shaders. So let's go ahead and go to the Vertex Shader, since this is the only one we're going to be messing around with. Our Vertex Shader is going to need 3 matrix 4x4s. In GLSL, it's called mat4. The first one will be called transform world. The second one will be transform object. And the last one will be called camera projection. We can have them multiplied together and then sent to the shader, but in future videos, we're going to be needing individual ones, like just the world's transformation, just the object's transformation. And so we're going to want to keep those separate anyway. Now what's next is we need to transform the position. We need to transform this vector 4 right here. So what we're going to do first off is we're going to take the first column of the transform world and we're basically going to add this with the second column, or not the second column, but the first row of transform object. And what we're doing is actually useless. Don't do that, because GLSL actually has this done pretty much behind the scenes, and it's just some basic matrix multiplication. all we have to do is do camera projection before our vec4, multiply it with the transform world, multiply it with transform object, and then multiply it with this vec4. Now we're almost done, except for one teensy little problem here. We have the variables defined, but OpenGL is going to treat these as variables that are internal, meaning that our program is not going to be able to edit these values like we want it to. All we need to do is add uniform in front. And this tells OpenGL, hey, these values are going to be edited by the program, and it's going to let us set these values now. So we're done with the Vertex Shader. All we have left to do is to go into the shader. To get started here, all we got to do is let's add in a couple integers. I'll call the first one UniMat projection, UniMat transform world, and UniMat transform object. The uni prefix is basically short for uniform. Inside this create method, at the end, all we got to do is set UniMat projection to GL get uniform location. And this is going to want our program, and it's going to want the name, which we have it named camera projection. Now, OpenGL is going to go through the program looking for this variable, and it's going to give us the location of it. If it can't find it, it'll return -1. We'll do this for the others as well. That should be it for the creation. Let's go ahead and create two methods. The first one being set camera, and the second one being set transform. Let's get started with the set transform. What we're going to do is we're going to create we're actually going to see if uniform mat transform object is not equal to -1. So if it's not equal to -1, then it exists in the shader. And now we can actually set these values. We need to retrieve the values first. And so we're going to create a float array. I'll call it matrix. And it's going to be set to a new float with the size of 16. Since 4 times 4 is 16. Then we're going to use transform.getTransformation .get, and then we'll pass in matrix. Then we can call GL uniform matrix for FV UniMat transform object transpose. No, we're not going to transpose. And then we'll pass in matrix. Okay, so why aren't we transposing? Well, since we're using JAML, and JAML is specifically designed for OpenGL, we're not going to need to transpose our matrix, which is basically just swapping the rows for the columns. If you are using a different math library, or perhaps even your own, you might want this to be true. I'm not sure. It's really dependent on how the library is or how you designed the library. So, but since we're using JAML, just leave it as false. We can actually go ahead and copy and paste this. I'm going to paste it twice. For the first one, we're going to use projection, camera, get projection. Then we'll use uni.mat transform world for this. Camera. Oh, yep. Get transformation. And that should be it. All that is left to do now is to go to the main and start dressing up your triangle. I will be right back with mine. Okay, so I basically have my camera and transform all set up. So the differences between the old main and the new main now is that I have created a camera and I have created a transform. For the camera, I had set it to a perspective with 70 degrees. We got the aspect ratio of our window right here, 640 divided by 480. 0.01 for Z near, and 1,000 units for Z far. Then I have the camera's position set to go up once and back 3. Up 1 unit, back 3 units. Now, you might be wondering, why aren't you using a -3? And the reason why we're not using a negative for the Z is because Jaml is doing things in right-handed coordinate system, which means forward Z is negative and backward Z is positive. Then I'm setting the rotation to -30 degrees along the x-axis. Then I have this float value here that increases every frame. And that is for the transformation set position, which is basically using a sine function for x. And also getting the rotation and rotating it by 1 degree every frame. Then I'm calling shader set camera and shader set transformation. And that's pretty much it. Let's go ahead, run, and take a look at the results. Look at that beautiful triangle. And that is all that is needed to transform your objects in 3D space. I hope to see you in the next episode where we begin to load in textures for the little triangle. I hope to see you there.